So this is the fifth video of Unit 3, and we're going to finish up talking about energy here, and then we will talk basically by kind of talking about total mechanical energy, and maybe doing some examples and stuff like that. After that, we're not quite done with energy just yet, but we're done with just the introduction part of energy. So after this video, I will make a video on conservation of energy, and then work kinetic energy theorem, and then also work energy theorem, and some videos for practice problems as well. So get ready for those. Okay, part 3, energy 3. This is where we talk about our total mechanical energy. Here are some learning targets. Last one, I know what total mechanical energy is. In the previous video, we stopped at, I believe we stopped at 0.7, so we'll pick up there. Or sorry, we ended on 6, and this is now 7. Let's double check. 7. Okay, so 7 was a summary. We'll call this part 8, or point number 8. And this is total mechanical energy. And I hinted at that. I used those words in the last video, but let's be clear on what we mean by total mechanical energy. So total mechanical energy is the sum of all mechanical energies. I will give total mechanical energy, I will give it one of two symbols. I'll use them interchangeably. Usually it will just be capital E. Sometimes it will be E sub T for total. Sometimes it'll be like E1 or E2 or E3 or E0, something like that. And these are still the total mechanical energies at some 0.1, maybe 0.2 in the motion, 0.3 in the motion, the initial one, maybe I'll use E initial, E final. These all mean the total mechanical energy at some time, but usually to start off with, we'll talk about just E, and then we'll start using like E initial, E final, and E with subscripts that are numbers in conservation of energy. So the total mechanical energy, E, is equal to T plus U. I said something about T being kinetic energy because of the French. U, I'm not sure why we use U for mechanical energy or for potential energy, but I think it has to do with voltage being V, and voltage is a difference in energy between two positions. And so a U is the energy. So if we do like U2 minus U1, that's equal to V. So we do T plus U, and then we also have this V, so it's TUV. I think it's just like a sequential thing. That's my theory, but I don't have any evidence to back that up. However, for our purposes, E is equal to T plus U. So total mechanical energy is equal to kinetic energy. Kinetic energy plus all of the potential energies, not just one, but all of them. So, and that kind of brings up another point where we can talk about our total potential energy. Actually, maybe we shouldn't make that a... Okay. Let's make that point D. Total mechanical energy. The equation for that is U, the total mechanical energy, capital U, is equal to US, U spring, plus U due to gravity. Once we get more mechanical energies available to us, like a rotational energy, stuff like that, it'll go into here, into one of these equations. But the idea is that if I take all of my energies that are potential and I add them together, that equals U. So for us now, that's U sub S and U sub G, and that's it. So when I talk about my total energy, my total mechanical energy, what I have is E is equal to T plus U. But T is just T, and U is U spring plus U gravity. Still equal to our total mechanical energy. And I can replace T. I know the equation for that. It's 1/2 mv squared. I know my spring potential energy. That is 1/2 kx squared. And I know my gravity potential energy, that's mgy. So if I plug all those in, I can calculate my total energy if I know my mass, my velocity, my spring constant, my stretch distance or compression distance, and my distance above the ground. So we don't always have every single one of these. If I'm talking about like a ball falling through the air or being thrown up into the air, I'd have to worry about mv squared. I'd have to worry about mgy, but I don't need to worry about kx squared. So when we set up one of these equations for conservation of energy and we talk about this total energy before or after the total mechanical energy of a system, we don't need to worry about every single one of them if there isn't a spring, or if it stays on the same surface, we don't need to worry about mgy. Because there's no change in that energy. And so we can define that position above the ground to be 0. And so your mgy just becomes mg times 0, which is 0. So anytime we have our energies, or we're talking about a system with energy in it, we have to be careful to pick out the ones that are good and just discard the ones that we won't need. I also gave you those equations in one of the previous videos for 1/2 kx squared and mgy. I didn't really tell you where they come from, but I'm going to say this. The energy of a system, where are we at, number 8? So energy, or maybe the energy of some certain type of energy, is the area under the force versus distance graph. And we talked about something similar to this, where the area under a curve was important to us. Maybe remember from Unit 1, we talked about how if I have a graph of acceleration, then I can find the velocity by calculating the area under the curve. We can do a similar thing with energy. So if I want to know what the energy is, then it is the area under the force versus distance graph. It turns out that if a force, and we can graph the force versus distance, we can figure out how much work that force does. And that's usually related to a change in energy too. So when that happens, our energy is the force versus distance graph, or the area under it, but also the work done by that force is the area under that graph. And you'll see why when we talk about the work energy and work kinetic energy theorem. But for now, the important thing that you should worry about is just calculating that area. Just like in our kinematics unit number 1, we had this situation where we would either have a triangle or we would have a square. And the similar thing is going to happen here. If I think about my force of gravity, Fg, and I think about maybe some distance y, I know that gravity, the equation for it, Fg, is mg. And so there's nothing about distance, right? There's no y in this equation, mg. And so no matter where I am, I will always have the same force of gravity acting on me. And so that's going to be a flat line. So if I start off at y equals 0 and I go to some distance y, my area under this curve, shade that in blue, is going to be a rectangle, the area of a rectangle, right? So it's going to be this width times this height. So area is equal to width times height. So width is going to be, y minus 0. So I just take my final minus my initial, and I get y minus 0, so that's just y. And my height is going to be mg, right? It's going to be how much force of gravity is acting on me. So I get ymg, or mgy. And that's where my equation for energy comes in, or for gravity energy comes in. For the next one, it was 9A, 9B. Energy is still the force, or the area under the force versus distance graph. So let's talk about this spring energy stuff. And that means that our axis up here is going to be the spring force, which is K times X. Okay, Now I know this equation, and we've plotted this, different stretch distances, and we used it to calculate the spring constant of a spring. But I know that this should look like a straight line, or a y equals mx plus b type of line. I know it should pass through the point 0, 0, because if I don't have a stretched or compressed spring, it doesn't exert a force. And so 0 stretch means 0 force, 0 compression means 0 force. And if I think about this area, it's going to be the area of a triangle, right? So this is area of a triangle, and that's going to be 1/2 times base times height. So I start off at x equals 0, I go to some spinal stretch distance x, and then my height is going to be k times x. So if I plug those in, I get 1/2 my base, which is x minus 0, times my height, which is k times x, and overall I get 1/2 times k times x, or actually it was, in order that we plug them in, it was 1/2 x times k times x, but I can simplify that as 1/2 kx squared, and that is where my equation for the spring force going into a spring energy comes from. There's more to it than that. It really requires us to do an integration, because anytime we talk about math, about this area under the curve stuff, we're implicitly talking about a integral. But for our purposes in the calc or the non-calc based physics, this should be good enough explanation that it's where it's come from. But if I want to go one step further and talk about this spring force and maybe the work that a spring force does, it would be F d cosine theta. Now let's just assume that the force and displacement are in the same direction, so the angle is 0 and cosine of 0 is 1, and so I get force times displacement. And I made this argument that half of the spring force is going to be exerted on the wall, and half of it is going to be exerted on the mass. So the force we plug into here is actually 1/2 times kx. That's our force, because only half of that kx spring force is going to be exerted on the block. The other half will be exerted on the wall. And the displacement, again, is x, and so I get 1/2 kx squared. And we can do a similar treatment for gravity. We said work is equal to F times distance times cosine theta, a distance displacement. I should say that I'm using these interchangeably. They don't really mean the same thing, but for our purposes, they do, because a distance, you can subtract that from 0 and get the displacement. But let's say that we're like seeing a ball, it's falling, force of gravity acts down, our displacement will be down, angle between them is 0, and so we'll get cosine of theta is cosine of 0 degrees, or just 1. And then for force, we'll have our force of gravity, mg. And for distance, we'll have y, right? We start off at some maximum y value, we fall down to some other y value, call this y2, y1, and maybe we could even call this change y2 minus y1, we could call this h. And so what I get is mgh, or mgy, and that is the equation for the force, or sorry, for the potential energy due to gravity. Okay, so now we've talked about total mechanical energy. We've talked about the different types of energies, and we've talked about the conservation of energy and conservative force. Well, we haven't talked about conservation of energy. We talked about conservative forces, though. But let's try a couple of examples just to pick out some information. So let's say that I have a chicken, and the chicken is crossing a horizontal road. Do a second one. Let's say we have a ball rolling down a hill. Also, about an airplane flying through the sky. Horizontally. This airplane, it's above the ground for sure, but it's flying horizontally. So I'm going to give you a moment. Go ahead and try to figure out what potential and what kind of energies are going to be present, whether it's kinetic, spring potential, or gravity potential. Try to come up with those, and I'll give you a moment or two to pause and work that out. Okay, should be back. So a chicken crossing a horizontal road. We can define that the horizontal position that they are at to be 0, and so our gravity potential energy is going to be 0 for that. But the type of energy it will have is kinetic, because it has a velocity. It will not have spring energy because there's no springiness to it, and so all we will have is just that kinetic energy. Ball rolling down a hill. This ball is rolling, so it has a velocity, so there's kinetic energy. It's also at the top of a hill, and so there's going to be a gravity potential energy as well. No spring, so no spring potential. An airplane flying through the sky horizontally. This is similar to a chicken crossing a road, right? It's flying horizontally. We can say that position is y equals 0, and so we don't have a potential energy due to gravity. All we have is a kinetic energy. This is if you wanted to. I mean, obviously, you could say that there is some gravity energy too, if you wanted to, but it's not necessary to do. When we talk about conservation of energy, you'll see why it just goes away. But it does. It just disappears when we do our calculations, and so there's no reason to even begin to consider it. However, if we really want to be thorough, we certainly could. So that is our talk on how to calculate energies, how to deal with energies, and it also is an introduction to total mechanical energy and a little bit of a talk about conservation of energy. So in the next video, we'll do is try to do some conservation of energy. Maybe we'll do some practice on it, and then we will move on to work kinetic energy theorem from there.